Demystifying self-sensing pumps. Variable speed pumping is bringing new levels of efficiency to the HVAC industry. The most recent innovation to this powerful technique is the family of Taco self-sensing pumps with variable frequency drives, VFDs. Users can set up a Taco self-sensing pump to operate in one of several variable speed modes or at a constant speed. These pumps eliminate the cost of external sensors. They enable system operators to quickly, easily, and economically balance their own systems and reduce outside contractor costs. This introductory video explains basic hydronic system design, the principles of operation of Taco self-sensing pumps, and how to select a pump for your hydronic system. For detailed information about the pump user interface, setup, and system balancing with a Taco self-sensing pump, please see other videos in the series available on the Taco website www.taco-hvac.com/self-sensing. What you need to know. To understand how self-sensing pumps work, there are some key elements of hydronic systems and components that you need to know. How a commercial hydronic system is designed, how to read a pump performance curve, how to read a system curve, how pump curves and system curves interact. Hydronic system design in brief. When an engineer designs a hydronic system, he or she begins by calculating the heating and/or the cooling load that the system will be required to handle. Here's a simple example system. Based on the load, the engineer has determined that this will be a 150-ton system consisting of a chiller and 5 fan coils. 4 of the fan coils are fitted with a 2-way control valve. The 5th has a 3-way control valve to assure that the system will have minimum flow. The system designer then chooses the delta T for the system. This is the temperature difference between the system fluid leaving the chiller and the return fluid. In this case, we'll say delta T is 12 degrees. The water leaves the chiller at 44 degrees and returns at 56 degrees. Basic hydronic system calculations tell the designer that a delta T of 12 degrees equates to 2 gallons per minute per ton, which makes the design flow of the system 300 GPM. The fan coils are all of equal size, 30 tons, and each requires 60 gallons per minute of flow. The HVAC engineer then lays out the system against the building's architectural plan to determine the total length of the system piping. From that measurement, he or she can estimate the pressure drop of the piping, components, and fittings. Standard HVAC calculations indicate that this system has 53 feet of head. The flow requirements and system head establish the system design operating point, 300 GPM at 53 feet of head. System curves. A system curve graphically illustrates the system head at any given rate of flow. In other words, a system curve shows the combination of flow and head throughout the operating range of the system. Once the system design operating point has been established, we can plot other points on the system curve using this formula. Head 2 over head 1 equals the result of Q2 over Q1 squared. Head 1 and Q1 represent the design head and flow of the system. Knowing those points, we can calculate system head at various flow rates. We can then use the data to generate a table and, in return, plot the system curve on a graph. Note that we've drawn the system curve based on the design operating point. As we will see later in this video, system curves change in characteristic ways when the system operates below its design point, in other words, at less than the maximum flow rate. Pump curves. Pump manufacturers generate pump performance curves by laboratory testing rather than by using a formula. The pump is mounted in a test stand. Pressure sensors are mounted before and after the pump. Then various instruments and controls are attached. A flow meter, a control valve or throttling device, a tachometer to confirm pump speed, a torque cell to measure horsepower, and a data acquisition console. The pump is then placed into operation. Here's example test data from a Taco KS pump tested at 1,760 RPM. For simplicity, we'll focus on just one impeller diameter, 8-inch, and 6 operating points. This data enables us to plot a performance curve for the KS4009. The curve is accurate for the KS4009 operating at 1,760 RPM with an 8-inch impeller. At any other speed and/or impeller diameter, a new pump performance curve will be created. How pump curves and system curves relate. Pump performance curves and system curves are independent of one another. However, the point at which they intersect at any given time provides the hydronic engineer with essential information about how that particular system will operate with this pump installed. Here's the system curve we plotted earlier for our sample system with a design operating point of 300 GPM at 53 feet of head. Here's the pump curve plotted for the KS4009 shown earlier. This pump and any constant speed pump can only operate on its performance curve. When we overlay the pump curve on the system curve, they intersect at the design operating point. As we can see by the movement of the system curve, as head in the system increases, flow decreases. As a result, the point where the curves intersect, which represents the system operating point at a particular moment, moves up and to the left on the pump curve. When the opposite occurs, as system head decreases and flow increases, the point at which this system curve intersects with the pump curve changes again, in this instance moving down and to the right along the pump curve. In effect, the system must accommodate itself to pump performance since the pump can only provide an operating point on its curve. The result is system inefficiency and wasted energy. Remember, the pump in this example is a constant speed pump. What happens when we replace that pump with a variable speed pump? Variable speed pumping. The way variable speed pumps operate is significantly different from how a constant speed pump operates. Manufacturers collect pump data in a similar way for variable speed pumps, but instead of testing at different impeller diameters, the pumps are tested at different speeds. There's only one impeller trim for each motor horsepower per model. For a pump with a variable frequency drive, such as the Taco SelfSensing pumps, pump speed is proportional to the frequency delivered by the drive. Lower the frequency delivered by the drive, and you lower pump speed. Raising the frequency causes the pump to pump faster. In the US, electrical power is delivered to the building at 60 Hz. Therefore, the rated speed for the motor is at 60 Hz. Here's a pump performance data table for the Taco 4007 self-sensing pump with a VFD delivering 60 Hz to the motor. At zero flow, the pump creates just under 57 feet of head and a little over 2 horsepower. As the flow increases, so does the horsepower, while the head decreases. At a flow of a little more than 360 GPM, the pump generates 49.5 feet of head and 6 horsepower. Here's a data table for the same pump with a variable frequency drive set at 40 Hz. Note that maximum head, maximum flow, and maximum horsepower are all lower because the drive is delivering power to the motor at a lower frequency. Here's the same data with a variable frequency drive set to 20 Hz. The data shows the same pattern. Taco collects 50 data points at various speeds for each pump, and the computer interpolates the data for all the intervening points that make up the pump performance curve. Variable speed pump performance curves. The performance curve for a variable speed pump is significantly different from that of a constant speed pump because of a fundamental difference between the two types of pump. Where a constant speed pump can only operate along its performance curve, a variable speed pump can operate anywhere along the curve or below it. Here's the performance curve for the Taco model SKS 4009 self-sensing pump. This pump can operate at any combination of flow and head in the shaded area of the graph. In other words, by varying its speed, the pump can deliver the precise combination of head and flow that the system requires at any given moment. The results are a big improvement in system efficiency, less wear on system components, and reduced energy consumption. How self-sensing pumps work. The key to the self-sensing pump's operation is the performance data that is collected before the pump leaves the factory. The head, flow, power, and speed information for each of the data points are programmed into the VFD. With this information in a lookup table within the VFD, the drive is now capable of operating at any flow and head within the range of the collected data table. Let's look at how the self-sensing pump responds to changes in system demand in our sample system. As the individual two-way control valves close, flow is reduced, head pressure increases, and the system curve bends up and to the left. Note there has to be a three-way valve or bypass valve in the system to ensure that there will be minimum flow. Now, let's overlay the performance curves of a self-sensing pump at 5 speeds, from 60 Hz maximum speed to 20 Hz the minimum speed. Operating the pump below 20 Hz may be detrimental to the mechanical seal and is not recommended. Therefore, the pump is programmed not to operate below this point. The pump can operate anywhere in the shaded area, but it must determine exactly at which point to operate in order to satisfy any given system demand. The pump determines that actual operating point minute to minute based on a control curve drawn for each pump individually. The control curve. The control curve is based on the design head and design flow provided by the purchaser when the pump is ordered. The pump is programmed to operate along this control curve to provide the greatest energy efficiency in a particular application. If the pump operates along a curve of any other shape, it will be less energy efficient. As we said earlier, a self-sensing pump changes its speed to accommodate the needs of the system at any given time. Let's see how that works. Here's a pump curve to illustrate. As demand increases, the system requires more flow. As the rate of flow increases, head decreases. The pump begins to ride to the right on the pump curve. However, as the system curve changes, the self-sensing pump automatically responds, in this case increasing speed, to keep the pump on the programmed control curve. A similar thing happens in reverse when there is less demand in the system. As flow decreases, pump head increases and the operating point rides to the left and up along the pump speed curve. The self-sensing pump automatically responds, slowing to keep the pump on the control curve, which keeps the pump operating at the most efficient point for system conditions at that time. Self-sensing pump operating modes. The Taco self-sensing pump can operate in one of several modes based on the shape of the control curve. In constant flow mode in the primary loop, for example, the drive will maintain the desired flow regardless of system resistance. The constant flow target is indicated by a vertical control curve. The drive will maintain constant pressure in similar fashion. The horizontal control curve indicates the drive is operating in constant pressure mode. It will maintain the same pressure regardless of system resistance. In a given variable flow and head application, the control curve represents the points of a theoretically most efficient system operation throughout the operating range of the pump based on the best placement of a differential pressure sensor as shown below. For more information, please see our video on control curves and setting self-sensing pump control modes. Self-sensing versus sensors. Until self-sensing pumps were developed, variable speed pumps required sensors at various places in the system to provide the feedback to control their speed. However, in practice, using sensors for this purpose is plagued by many problems. Sensors are frequently placed in the wrong location in the system, and incorrect sensor placement results in system inefficiency. Typically, sensors must be physically moved from one location to the other, searching for the correct placement. This can be costly and is often impractical. Additionally, even when the sensor is correctly located in the system, a correct set point is rarely used. A differential pressure sensor located near the pump discharge won't save much energy. On the other hand, a differential pressure sensor placed at the farthest, most significant load will save the most energy. The set point must be equal to the pressure drop at the sensor location at design flow. The result is a significant savings in energy consumed. In comparison, Taco self-sensing pumps do away with pressure differential sensors and all the problems associated with them. Guided by its control curve, a self-sensing pump maintains the most efficient operating point to meet system requirements at any given time. You no longer have to move sensors to a new, more optimal location in the system. The self-sensing pump enables you to quickly adjust the control head as needed to achieve greater system efficiency. Selecting a Taco self-sensing pump. The Taco Pump Selection app makes it easy to select the right self-sensing pump for any application. The app is available on the Taco website www.taco-hvac.com. To select a self-sensing pump, open the app on your mobile device or access from the app's drop-down menu on the Taco site. Follow the steps on the left side of the page. Choose Self-Sensing Variable Speed Pump. Then enter the design flow and design head. We'll enter the values from our sample system, 300 gallons per minute at 53 feet. Choose the various options available for pump speed, motor, and units of measurement. Leave thumbnail on the default setting of performance curve. Next, choose the types of Taco variable speed pumps to include in your search. Then click Search. The Pump app displays the pumps that meet your performance criteria. Let's click on SKV SKS 4009. Click on the pump model number. The app displays a pump curve, pump specifications, and the documents related to this pump that are available on the Taco website. Click the graph for a bigger view. You can also choose a different available horsepower and enter a new value for the control head. Check the Constant Flow Curve box to display a graph with a new curve displayed. You may download the pump performance curve generated and any of the related documents shown. This concludes demystifying self-sensing pumps. For more information on the setup and operation of these pumps, please see the other videos in this series available on the Taco website.